So let's talk about this issue, or at least something that this is related to. The second biggest problem in machine learning after overfitting is what is called the curse of dimensionality. And again, the curse of dimensionality is present with every method, and affects the more powerful ones more, as usual. But it's a particularly severe problem in instance-based methods, which is why we're going to talk about it here. But again, just as we introduced overfitting with decision trees, but now it's going to apply everywhere, the curse of dimensionality is also going to apply everywhere. So this is a general issue, not just with instance-based learning. Okay? You remember when I said that if somebody asked you, what is the problem with this machine learning algorithm, and you didn't have an answer, a good thing to just say is, overfitting. If overfitting fails, your second best choice is curse of dimensionality. And between overfitting and curse of dimensionality, you probably get a lot of things right. So, good thing to remember. So what is the curse of dimensionality? Okay? And by the way, the curse of dimensionality affects other things besides machine learning. It was initially, the term was coined by a famous control theorist called Richard Bellman. Because he had these methods for optimal control that worked fine as long as you were in low dimensions. And when the dimensions got high, everything fell apart. And he called it the curse of dimensionality. Right? So what is the curse of dimensionality? Let's look, here's the first instance of the curse of dimensionality. It's something that we've already alluded to. Let's suppose that your instances are described by 20 attributes, okay? But only 2 of those are relevant to predicting the class. Remember our parity example, right? Your class is the parity of 2 of the bits, but then there's 18 irrelevant ones. For nearest neighbor, this is a really serious problem. Nearest neighbor isn't going to pick out the signal from those 2 attributes out of the noise from all those other 18. Sure, those 2 are pointing in the right direction, but superimposed on that is a noise signal that's an order of magnitude larger than we're host. Okay? This, as I mentioned, is the single biggest problem with instance-based methods, and is the single biggest reason, or at least one of the biggest reasons, that people use other things like decision trees and whatnot. Okay? At least from the point of view of accuracy. Okay? And this is an example of the curse of dimensionality, because if the dimensionality was low, you wouldn't have this problem. Right? If you just had 2 irrelevant ones, well, given enough data, you'd probably be able to pick out the right ones. But if you have a lot of irrelevant ones, then you are host. Okay? However, it gets worse, much, much worse. Here's the shocking thing. Let us suppose that instead of 2 relevant attributes and 18 irrelevant ones, I had 20 relevant attributes. Does this mean that I'm in better shape than with 2 relevant attributes? What does your intuition say? Would I rather have more information about my customer or less? More, right? Don't be afraid to state the obvious, right? Of course, this is a trick question. Yeah, there's a catch somewhere, right? So, we can do this on these 2 levels, right? So, on the one hand, surely knowing more about your customer is better, right? But here's the thing, is as I go into higher and higher dimensions, right, my space gets bigger and bigger, and my examples get farther and farther apart. And if you think about it, what I need for instance-based learning to make good prediction, as we just saw in the theory part, right, is I want my nearest neighbor to be close to my point, right? As long as the class probabilities don't vary too suddenly, if my nearest neighbor is close to the query point, there's a good chance it's going to be right. Okay? And the problem with being in very high dimensions is that in high dimensions, everything is very far from everything else. And so as you add more dimensions, yes, on the one hand, you have more information, which is good. But on the other hand, it becomes, the whole notion of who's closest to you becomes very fuzzy. And so the thing that's perverse is that the curse of dimensionality hits you even if all the attributes are relevant. Now, if the attributes are highly relevant, right, if each one of these attributes is a very strong predictor of the class, then this won't happen. But then you don't need, a lot of them anyway, right? Then many of them are, redundant or irrelevant. The problem, but then what you want to use is probably something like a decision tree that will, you'll build a tree over those attributes and ignore the others. But if what you have is a situation where you have a lot of signals, but they're all weakly predictive of the class, then they're all relevant, but now you're really in this situation where you might do well, except for the fact that the curse of dimensionality might kill you. The signal is there, right? But it's very diffuse, right? And this is when things become difficult. Okay. So In high dimensions, nearest neighbor is very easily led astray. Its ability to discriminate basically dies down as we get to high dimensions. We're going to see some examples that hopefully will make clear why this happens. More generally, not just with nearest neighbor, with lots of different techniques that we use in machine learning, with optimization techniques, right? In machine learning, the final step is always to optimize. Optimizers often work well in low dimensions. In high dimensions, things are much, much harder. Okay? And finally, here's the biggest issue of all. The biggest issue is in our brains. Is that we build all these machine learning algorithms and all these techniques based on our intuitive understanding of a three-dimensional world. Right? The real world is 3D. Your brain works in 3D. Your visual system with all of its power works in 3D. As long as we're in 3D, we're happy. Right? We have a really powerful machine inside our heads for dealing with three-dimensional space. But the problem is that in most machine learning situations, you're dealing with 100, 1,000, 10,000 dimensional space. And the thing is that in 1,000 dimensional spaces, things are very, very different from what they are in 3D. And the intuitions that you have from 3D and 2D do not carry over. In fact, very weird things happen in high dimensional spaces. And so all the intuitive things that we might do with nearest neighbor, we always have to, be on our guard. Because your intuition could be leading you astray. Okay? This is the biggest problem. This is what makes it hard to design, these algorithms. And as I mentioned before, there's a famous data mining, researcher who says that if people could see in high dimensions, we wouldn't need machine learning. But we can't see in high dimensions, and that's why we need it. So let me just give you a few examples that hopefully you'll find entertaining as well as instructive of why low-dimensional intuitions do not apply in high dimensions, right? So the first example is the example of our good old friend, the normal distribution. Okay? What could be more basic than the normal distribution, right? So let's look, first of all, at a normal distribution in one dimension, right? A normal distribution in one dimension looks something like this, right? Here's my x, and here's my p of x, right? And it's our famous bell curve, right? And here's my mean, right? And if I draw a band of one standard deviation around the mean, something like this, right? Most of the probability mass is there, right? Minus sigma plus sigma, right? One or two standard deviations, right? The whole idea of a normal distribution is that most of the probability mass is concentrated around the mean, right? And then there's some fuzz around that mean. But roughly speaking, I know that I'm going to be landing near that point, right? This is the very meaning of a normal distribution, okay? Very good. So, now let's see what happens in 2D, right? And in 2D, let's look at this from the top, right? So what I'm going to do is I'm going to put x here and y here, right? And now I'm going to represent, the distribution using curves of isoprobability. So, all the points around here have the same probability, right? The maximum, of course, is still here. Let's say that I'm centering this at the max. Let's say it's 0, for example, right? And so these are bands of equal probability, right? So in reality, in 2D, this is going to look like a bell, right? Like a real, 3D bell, right? And now let's look again at my band of one standard deviation around the mean, right? That is still where most of the probability mass is, right? But notice the following thing that has happened. A smaller fraction of the total probability mass is now within a radius sigma of the mean. Here, it really was a big chunk of the whole distribution. Here, it's a smaller chunk of the whole distribution. Right? Just looking at that, hopefully you can see, right? This now accounts for less than my probability mass than what I had before. Even accounting for the fact that, that it's rising higher there, right? Because there's all this space around here that the lower probability can happen in. When you add up the low probability over that entire big section of the plane, well, that adds up to a lot. And now, of course, you can see where this is going, right? Let's do this in 3D, right? Now what I have is these spheres, right? And there's a sphere that's here within one standard deviation of the mean. And now this sphere is starting to be a pretty small fraction of the whole. So even though the probability is higher there, more and more of the probability is outside of that region. And guess what happens if you go to sufficiently high dimensions? And that doesn't even have to be very high. for reasonable, variances. You know what's going to happen? Is that most of the mass of the probability distribution is far away from the mean. This is a really disturbing thing, right? You have a normal distribution and most of the probability mass is far from the mean, right? This is exactly the opposite of how we think of a normal distribution. And yet it's what really happens. This is the curse of dimensionality. You're picturing the normal distribution as meaning one thing because of your intuition in low dimensions, but in high dimensions something very, very different is going on. Okay? Any questions or thoughts on this? Okay, but it doesn't end here. After all, this could just be, it's an odd thing that happens with a normal distribution. Unfortunately, it's an odd thing that happens with just about everything in high dimensions, right? In high dimensions, it's like this Alice in Wonderland quality to everything that goes on. It's like the Twilight Zone. Weird paranormal things start to happen. So here's another example. Oops. The uniform distribution on a hypercube, right? Very natural thing, right? I have a hypercube. Let's just think of a cube, right? I have a cube here, and my points are normally distributed inside it, right? So most points are going to be in the middle of the hypercube. There's going to be very, very few points that are on the walls of the hypercube, right? Let's say that we define a band of, with epsilon, where epsilon is very small, only near the walls, right? Very few of the data points are going to be in that band of size epsilon near the walls, right? Most of them are going to be in the middle, correct? Well, guess what happens in high dimensions? In high dimensions, almost all the points are within that band epsilon of the walls. In high dimensions, if you have a uniform distribution over the hypercube, most of the points are close to one of the walls. For the same type of reason why the normal distribution's mass, goes outside. Because there's just so much volume near the walls, right? This is the thing that our intuition doesn't quite capture. In 3D, most of the volume is inside. It's not near the walls. But in high dimensions, there's a lot of volume near the walls. And think about what this means for nearest neighbor, right? For nearest neighbor, you don't want your points to be near the walls because on the other side of that wall, there's nothing. You can't classify those points well. So as long as all the points are safely in the middle, right, then you can probably classify them all. If your points are near the wall, things start to get dubious. And yet that's what's going to happen to almost everybody once you're in sufficiently high dimensions. Okay? So this is our second slightly disturbing example. Here's a third one, a hypergrid. Okay? So what is a hypergrid? Let's start with a grid of dimension 1. Okay? So this is just a line, x, and I'm going to put my points evenly spaced on it. Okay? Forgive my poor drawing. Okay? So let's say that this is discretized, right? So I'm kind of simplifying my life by discretizing my space. This should make life easier for nearest neighbor, right? Okay, very good. So let's suppose that this is my queer point over here, right? And who's my nearest neighbor?
There's a point to your left or right.
There's two, right? There's one to my left, and then there's one to my right, right? They're equally distant, and there's a tie between those two guys. Okay, so if I wanted to use nearest neighbor, I would have to break the tie between those two, right? But this doesn't sound so bad, okay? But you know where this is going, right? Now let's see what happens in 2D, right? Now in 2D, what I have is a grid like this, right? Right? Actually, let me draw one more. And now here's my x cubed, right? So who are my nearest neighbors now? If I want to find my nearest neighbor, who ties for nearest neighbors? 4 points, right? The one above, the one below, the one to the left, and the one to the right. Uh-oh, I'm getting a 4-way tie for nearest neighbor. This does not look good, right? What happens if I am now in a hypercube? How many, equally near neighbors am I going to have? I'm going to have one above, right, one below, one to the left, one to the right, one forward, and one backward, right? So here I had 2 nearest neighbors. Now I have 4, and now I have 6. So in D dimensions, how many, equally close nearest neighbors am I going to have? 2D. So if I'm in a 100-dimensional space, I have a 200-way tie for nearest neighbor. That doesn't look so good. Okay, you see the problem? The whole notion of nearest neighbor starts to become meaningless, basically. The whole notion of similarity and distance and, classify using the one that's closest, is like what? There's all these hundreds of points that are equally close to you. Right? If I have 100,000 dimensions, which, these days is not rare, I have a tie between 100,000 points. Bad news. Okay? So, 2 more quick examples, particularly relevant to machine learning, at least the first one. Let's say that I'm going to approximate a sphere by a cube. Okay? This, for example, is what's going to happen if my data lies in a sphere, and I'm going to learn that with a decision tree, right? I'm going to form a cube around that sphere, right? And this sounds reasonable, right? Well, a cube is a reasonably good approximation of the sphere, right? It's not exactly right, but it kind of captures what's going on, right? So let's see what happens in this case, right? So first of all, in 2D, right, here's my sphere, and here's my cube, right? And so let us shade in the area where we get things wrong, right? It's this area, right? And now let's do this in 3D, right? Now in 3D, now there's a cube, right? And the sphere is inside the cube, right? What has happened to the area where things go, to the volume where things go wrong? Has it gone up or down?
It's gone up.
It's gone up, right? And guess what happens if I go to a 4-dimensional hypercube? These things are hard to visualize, but let's do the following, right? Let's represent this. Let's represent the sphere by just a circle in 2D, and let's represent the square by 4 points like this. Let's make it a star, and make the size of these points, these triangles, proportional to the volume of air. Okay, you get the idea? So what happens in very high dimensions? Can anybody guess? You can probably guess by now what's going to happen, right? I'm going to see something like this. There's this little tiny circle here, and then there's like these points of air like this. The volume where I'm accurate is dwarfed by the volume where I go wrong. In 2D, sure, my hyperplanes that my decision tree forms were a fine approximation. In 3D, still okay. In 100 dimensions, it's a terrible approximation. When I approximate that hypersphere as a hypercube, almost all of the volume of the hypercube is where it should not be. It's outside the hypersphere. Okay? High dimensional is a very disturbing world to live in. So finally, we could go on with these examples forever, but let me just give a quick final one, right? Think of an orange, right? An orange is roughly a sphere, right? And, the orange has its skin, right, which you don't want to eat, and then it has the pulp, which is the good part, right? So, what do you think a high-dimensional orange looks like, a hyper-orange, right? What do you think is the volume of the skin versus the volume of the pulp? Which one is going to be larger?
More skin than you had in 3D.
Exactly. So in high dimensions, the volume of the skin is going to be larger than the volume of the pulp. In fact, if you take you can do this as an exercise. Work out the formula for the volume of a hypersphere, right? And then, think of the volume of a region of size epsilon, close to the hypersphere, so the skin of the orange, and see what happens as you take the dimension to infinity. You know what's going to happen? The fraction of the orange that is pulp goes to 0. If the dimension is sufficiently high, the orange has no pulp. It just has skin. There's nothing left to eat. That's a kind of funky orange to have. But that's the world that we live in when we do machine learning. Please don't have nightmares about this tonight. We don't want to have a negative impact on your mental health.
Giant orange. That's what I remember from the class.
Yeah, that's right. 20 years from now, right, when you're old and gray, you're like, I don't remember anything from the PMP course, but I remember that disturbing orange that was all skin and no pulp. Yeah. We will resort to anything to make you remember the stuff in this class. Okay, so hopefully we've illustrated why the curse of the dimensionality is such a big deal. Right? There's all these ways in which it comes at you. Curse of dimensionality really is one of the top two things that makes life hard for you.